Good afternoon, everyone, and welcome to the latest in our Down to Earth series of webinars, which today is being given by my colleague Mel Lyons, who's going to be giving us a presentation on managing uncertainty in groundwater risk assessments. But first, I'll just go through some brief housekeeping. So all attendees' microphones are automatically muted, so we can't hear you. Hopefully you can hear us. During the presentation, you can post questions and we'll have a Q&A session at the end. We'll answer as many questions as we can, but if there's anything that we can't answer, we'll try and get back to you individually afterwards. Shortly after the webinar, you'll receive a questionnaire, a link to a short survey. So if you could fill that in for us, that'd be much appreciated. So with further ado, I'd like to introduce Mel. Mel is a chartered geologist, a Silk and SOBRA accredited risk assessor for controlled waters, and she works in RSK Geosciences Southampton team. Mel's been with RSK since 2007, with the exception of a brief 2-year foray in the world of environmental regulation with the Northern Ireland Environment Agency while she was living in Belfast. Her specialism is hydrogeology and detailed quantitative risk assessments, producing sustainable risk-based management solutions for a wide range of projects across the UK, Europe, Middle East and Africa, and for clients ranging from small-scale private developers through to large-scale development corporations and international oil companies. So without further ado, I'll pass over to Mel.
Thank you, Mark. I'm going to switch my camera off for the duration of the presentation, but then we'll switch them back on again for the questions at the end. So thanks for the introduction, and thank you all for joining us today. I'm going to talk to you, as Mark said, about managing uncertainty in groundwater risk assessment. But before we start, I'd just like to say a quick thank you to a couple of my colleagues, Francis and Helen, for helping prepare this presentation, and also to Francis in our events team for her support in getting us online today. So when we're managing uncertainty in groundwater risk assessment, it won't come as a surprise to us that the first and foremost aspect that we need to consider is making sure that we obtain good quality data, and this is fundamental to developing our understanding of the aquifer characteristics. Today I'm going to take you through a series of case studies that aim to highlight where common areas of uncertainty can lie and how we can target our work to reduce or manage those uncertainties, and in doing so produce representative models of groundwater plume migration and realistic assessments of potential risks whilst maximising our clients' budgets. So the 4 key aspects that we're going to look at today include the development of our conceptual understanding of the groundwater regime and the connectivities between the groundwater and surrounding surface water features, also looking at examining water quality parameters and how they can help us characterise contaminant degradation. We're also going to have a quick look at the value in conducting suitable in-situ hydraulic conductivity tests to ascertain site-specific aquifer properties and some of their limitations, and then also a quick look at reviewing the resource potential of a particular groundwater body and how that may affect our remediation options. So the first of those aspects, developing our conceptual understanding of the groundwater regime, we're going to look at a case study, which is a vehicle manufacturing site located in the southeast of England. So RSK were requested to get involved on this site and review a raft of previous investigation information relating to the 30-hectare former vehicle manufacturing site. The site was proposed for a large residential development, including community facilities, schools, and commercial properties. Overall, a total of 24 previous investigations have been completed across the various land parcels that made up the site. But crucially, there was no single report available for them to submit to the planning authorities, which summarised all of the work that had been completed within the site boundary. And similarly, an overall remedial strategy was also required that encompassed the whole site rather than individual land parcels. So in terms of the site setting, specifically the controlled waters receptors, in reviewing the site setting, numerous potential controlled waters receptors were identified. There was a river running from north to south through the centre of the site, with an infilled canal adjacent to the west. There were also several surface water features located to the south of the site, including a tidal primary river located around about 1.5 kilometres to the south of the site, and the on-site river was a minor tributary to this primary river. And then around about 150 metres to the north of the site, there was also the outer limit of a source protection zone. So in terms of the site geology, the site's underlain by various water-bearing strata, as we can see summarised in the table, with a basic geological sequence comprising made ground with pockets of perched groundwater within it, followed by alluvial deposits comprising cohesive layers with a peat horizon in between, and this horizon was classified as a secondary undifferentiated aquifer with flow within that water body towards the on-site river, so west or east depending on which side of the site we were on. Underlying the alluvial deposits, we moved into river terrace deposits, which were predominantly gravels, classified as a secondary A aquifer, with flow within those river terrace deposits towards the south, consistent with the direction of the river flow and the regional groundwater flow within that water body. There was also a small 40 mil tidal fluctuation noted within the river terrace deposits groundwater levels, suggesting continuity with a tidal river that's located off-site to the south. Moving through the river terrace deposits, we encountered Lambeth Group and Thanet Sands, both of which were classified as secondary A aquifers, and groundwater data within these water bodies inferred at least a degree of hydraulic continuity between the two groups, and the flow direction within these deeper water bodies was actually towards the north, towards the source protection zone. In the areas where the Lambeth Group was absent, the river terrace deposits had comparable water levels to those within the Thanet Sands, suggesting potentially an element of continuity between the two water bodies in those localised areas. But overall, the potential for connectivity between those water bodies had to be considered in this location. But generally, the flow within the river terrace deposits was south towards the river. Finally, although not encountered on the site, the underlying bedrock at depth comprised the Upper Chalk Formation, which is classified as a principal aquifer, and regional data indicated a flow towards the north in this deeper water body, again towards the source protection zone. So as we have seen, there are several water bodies present beneath the site, some of which are in continuity with each other and some of which are only partially or locally connected. So in order to inform our conceptual site model further, we completed a survey of the river water levels and compared these levels to groundwater levels measured in nearby monitoring wells that were installed within the various strata. The results of this survey, as you can see on the cross-section here, show that the perched water levels within the made ground were generally perched well above the varying river water levels. Moving into the alluvium deposits, represented by the orange line on the cross-section, these were noted to be only marginally above the higher river level, but well above the lower level of the river. And then moving into the river terrace deposits, the green line on the cross-section, we were able to infer that these river terrace deposits, the groundwater within the river terrace deposits, was in continuity with even the lowest levels of the river level variations. And then, although not so shown on the cross-section, the survey of the base of the river level was indicated to be well above the level of the Lambeth Group and underlying Thanet Sands. So overall, the assessment suggested that groundwater within the river terrace deposits and the alluvium under some conditions is likely to be in continuity with the river, whereas perched water within the made ground, and again the alluvium to some degree, may simply drain into the river. Whereas in terms of the deeper water bodies, the water levels within the Lambeth Group and the Thanet Sands were well below the base level of the river, further suggesting a lack of continuity with the surface water feature. And these characterizations were also supported by the groundwater flow directions as characterized on the previous slide. So going back to the review of the previous investigation reports, which included a detailed quantitative risk assessment, we were able to make some key observations with respect to the various understanding of the groundwater regime and the subsequent assessment of the potential risks to controlled waters. There seems to be a limited consideration of the relevant potential controlled waters receptors when identifying the relevant assessment criteria to be used in the assessment, i.e. whether we're talking about drinking water standards or environmental quality standards. when looking at the water bodies beneath the site, regardless of the connectivity with the principal aquifer underneath or the flow direction towards the source protection zone, highly conservative drinking water standards have been assumed across the board and applied in all of the assessments. There was also minimal consideration of the brackish nature of the underlying groundwater, and also the fact that the site was located in a highly industrialised area. Therefore, the wider water quality and therefore also its resource potential was also known to be low, but this hadn't been considered in the derivation of assessment criteria. So as a result, the previous DQRA that had been completed had derived some immediate targets, but these were considered unachievable and unreasonable. And it was therefore concluded that based on our updated understanding of the groundwater regime, there was some refinement that could be completed on the conceptual site model and the conclusions of the risk assessment. So based on our updated knowledge, and in particular our understanding of the relevant receptors and their continuity with groundwater, the following updated conceptual site model was generated for the site in order to complete the first step of the risk assessment, the generic quantitative risk assessment. The key here was considering the relevant pollutant linkages based on each groundwater body and assessing the contaminant concentrations present within those water bodies against appropriate GAC, depending on the relevant pollutant pathway and the receptors in question. So for the made ground, the alluvium and the river terrace deposits, this comprised an assessment of leachate and groundwater concentrations against environmental quality standards that were designed to be protective of the transitional estuarine and coastal waters, given our understanding of the continuity between these water bodies and the surface water features on and off site. And then in terms of the underlying Lambeth Group and Thanet Sands formation, these were assessed against drinking water standards designed to be protective of the SPZ to the north and the fact that groundwater direction within these water bodies was flowing towards that SPZ. In addition, an assessment of the regional water quality for each contaminant was also undertaken in order to assess the wider background concentrations of the various contaminants in the area. Many of the contaminants that we had been considering were in fact found to be regionally elevated, so the upgradient concentrations on the upgradient site boundary were comparable to those on the downgradient site boundary, showing minimal variation across the site. And on this basis, remediation on the site-specific scale was not considered to be warranted, as further ongoing risks to the surrounding aquifer was considered to be low. Instead, our assessment focused on key contaminants of concern, namely the risk drivers, from which the site was contributing additional contaminant load to the wider water body. So the overall objective shifted from remediation to specific targets towards an overall betterment of groundwater conditions. A subsequent updated DQRA was undertaken that considered concentrations of xylene and ethyl benzene in the perched water in the alluvium, as well as concentrations of mid-range aromatic hydrocarbons that were also present in the perched water. And then additional investigation was also completed to investigate potential presence of solvents and possible DNAPL within the deeper groundwater bodies. So moving on to the second point that we're considering today, we're looking at examining water quality parameters and how they can help us characterise contaminant degradation. So the collection and interpretation of water quality parameters is key to characterising natural attenuation processes within the aquifer, and it's vital to understanding the key processes that may be contributing to the degradation of contaminants in the subsurface. To characterise the potential for natural attenuation to be occurring, a robust conceptual understanding of the site is required in the first instance, including aspects such as the geology, the aquifer conditions, and also the contaminant concentrations and the potential for daughter products to be generated. In particular, we can complete some fairly straightforward in-situ monitoring during sample collection that can provide us with beneficial water quality parameters that can provide a line of evidence towards understanding the potential for natural attenuation to be occurring. And when assessing the attenuation of hydrocarbons, for example, the following water quality parameters should be collected in the field as a minimum, including aspects such as pH, dissolved oxygen, redox temperature, and electrical conductivity. So, of these parameters, assuming that the groundwater pH is within the acceptable range to support biodegradation, 6 to 8.5, then we can look at the redox and the dissolved oxygen concentrations, and these will provide information on the type of metabolic pathways that are likely to occur in the aquifer. So firstly, considering dissolved oxygen, we know that anaerobic degradation is unlikely to occur with dissolved oxygen concentrations above 0.5 milligrams per litre and will not occur at concentrations above 1 milligram per litre, whereas aerobic degradation requires the dissolved oxygen to be above 1 milligram per litre. Similarly, looking at the redox values, we would expect to see mildly reducing conditions where our redox values range from minus 150 up to plus 50 millivolts, and then strongly reducing conditions below minus 200 millivolts. Similarly, above 150 millivolts, we would expect to see oxidizing conditions. In terms of groundwater temperature, biodegradation will be slower at lower temperatures, and this can also affect the solubility of contaminants. So within the UK, considering our groundwater temperature is usually in the range of 8.5 to 11 degrees C, temperature can be a key factor when looking at biodegradation potential. And finally, in terms of electrical conductivity, this can be used as a general water quality parameter used as a marker to verify that the samples have been obtained from the same aquifer system to make sure that we're considering comparable samples. So as well as the in-situ aquifer data, we can also analyse our groundwater samples via laboratories for geochemical indicators of natural attenuation. To interpret these results, we consider that decreases in the concentrations of electronic receptors and corresponding increases in the concentration of metabolic byproducts provide indirect evidence for degradation. Visual plots of the electron receptors variation across the site or byproducts can also help us visualize plume behavior, providing evidence for a shrinking, stable, or expanding plume. As an example, referring to the aspects within the table, we would normally expect mildly reducing conditions to be associated with denitrification and manganese reduction. Subsequently, as the environment becomes more reducing, biological degradation continues on the basis of ion reduction, sulfate reduction, and methagenesis sequentially. A couple of points to watch out for when we're trying to interpret our geochemical laboratory data. With respect to denitrification, the increase in nitrate within groundwater as a result of denitrification is rarely observed in our laboratory data. However, the relative reduction in nitrate concentrations within a plume is often noted, particularly when compared to higher background nitrate concentrations. And also an important point to note should be that when we are using preservatives and filtering our groundwater samples on site, this can play a big part in the collection and analysis of representative samples. When preservatives are used, the samples should always be filtered to prevent the leaching of compounds which may be sorbed onto soil particles and therefore otherwise potentially skewing our data. So to have a quick look at how geochemical and in-situ data can help us with characterising the degradation regime beneath the site, we're going to have a look at another case study, which is a petrol filling station located in Kent. It's an active petrol filling station in a mixed residential and commercial setting with the closest residential properties in the region of 20 metres south of the site. There's a primary river located 900 metres north of the site and also the boundary of an outer source protection zone associated with an abstraction located several kilometres to the west of the site. Previously, a programme of soils remediation had been implemented at the site due to historical fuel releases, and remediation had been undertaken as far as possible given the site constraints, but nevertheless, some residual contaminants remained on site in the groundwater. So in order to assess the effectiveness of the remedial works and the impact of leaving this residual contamination in situ, a long-term programme of groundwater monitoring and monitored natural attenuation was commenced. The objective of this work was to understand the site groundwater conditions for the purposes of continuing environmental stewardship on the site. So in terms of the site-specific setting, the site's underlain by various geological strata, as shown in the table. Much of the site was underlain by made ground, moving into silty and clayey sands and gravels at the Taplow gravel formation, which was classified as a secondary A aquifer and noted to be dry during the drilling works. Underlying the Taplow gravel formation, we moved into chalk bedrock of the Seaford chalk formation and the Newhaven chalk formation, which was encountered as putty chalk becoming more intact with depth. A groundwater body was noted within the chalk, with strikes during drilling starting at around 8 meters and rising to 5 meters below ground level, with flow within the groundwater body towards the north in the direction of the primary river and the source protection zone. The groundwater data also identified dissolved phase concentrations of BTEX compounds, of benzene, toluene, ethyl benzene and xylene within groundwater in various areas of the site. So I mentioned earlier that generating spatial plots of various parameters can aid in the visualization of plume dimensions and evolution. And to this effect, the following figures, which were created using the open source GWStat software, represent plume plots of dissolved phase benzene concentrations generated using data collected over consecutive years between 2012 up to 2015. As you can see from the plots, they show two distinct areas of elevated benzene concentrations within the groundwater, one to the north of the site and one in the south of the site, albeit noting that there is a gap in the well coverage within the centre of the site due to site constraints from below ground infrastructure. So considering the full range of data, which in fact dated back to 2004, it was apparent that the down gradient northern plume had shown continuous reduction since 2004, with only limited concentrations remaining during the later monitoring rounds up to 2015. Whereas the up gradient, the southern plume area, whilst this has also reduced, is to a lesser extent and appeared to be stabilising in more recent years. Now, at the same time as the groundwater samples were being recovered by low flow groundwater sampling, we were also able to measure water quality parameters. And a review of the dissolved oxygen and redox concentrations indicated mildly anaerobic to anaerobic and reducing conditions within the plume core, so within the north and the south of the site. And these conditions transitioned to more aerobic and oxidizing conditions on the plume fringes. The samples were also analysed for various geochemical parameters, as we saw on the previous slide, and these included dissolved methane. And the plots on the screen indicate over the same time period as we had the dissolved benzene concentrations, the variation in dissolved methane concentrations across the site. The methane plots in particular indicate falling concentrations of dissolved methane outside the plume areas since 2012. But within the north and the south of the site, where we had the elevated benzene concentrations, we had consistently high methane concentrations throughout the monitoring period. And the presence of these sustained elevated methane concentrations was considered an indicator that methanogenic processes are occurring within those plumes. And this ties in with the earlier data, the dissolved oxygen and the redox data, that indicated anaerobic and reducing conditions within the aquifer. So based on the evidence for ongoing natural attenuation, an assessment of the biodegradation capacity of the system is undertaken, considering the total BTEX concentrations beneath the site, in order to understand the potential for that natural attenuation to continue. Assessing the biodegradation capacity provides us with an indication of the amount of a contaminant that can be theoretically degraded by a particular electron accepting process at a site. And the assessment comprises calculating the difference in concentrations of the various electron acceptors at the up hydraulic gradient site boundary, so considering the background aquifer conditions, and also looking at the conditions within the plume, and then dividing them by a utilization factor, which considers the preference of the various electron acceptors and being utilized by the microbes. And this is a standard literature value that varies depending on the compound we're considering. And this is detailed within the Environment Agency R&D P95 document. So based on the calculations, we were able to characterize that the aquifer could theoretically provide the capacity for degradation of up to 17.7 milligrams per litre of total BTEX, compared to our on-site maximum concentrations of just 0.36 milligrams per litre. And overall, we were therefore able to reach the conclusion that the biodegradation capacity of the system is sufficient to degrade the present concentrations, with the primary mechanism in this instance being methanogenesis. And on this basis, we were able to conclude that given the lines of evidence provided, continued natural attenuation of the residual BTEX compounds was feasible, and that no further remediation was likely to be required. So moving on to the third point, looking at in-situ hydraulic conductivity tests. So the identification of a representative hydraulic conductivity, or a K value, for an aquifer is another way that we can aim to minimise uncertainty in our risk assessments. If we don't have site-specific data, we're forced to rely on literature source values for typical geological strata, and these values can often range across several orders of magnitude, and it's simply down to professional judgment as to which value we select. The aquifer hydraulic conductivity is a highly sensitive parameter in contaminant fate and transport models, and it's important if we can constrain this as far as possible. As an example, when we're considering a level 2 DQRA assessment, which considers the dilution of a contaminant as it enters the groundwater from the unsaturated zone, areas with a higher hydraulic conductivity result in greater dilution being attributed to more permeable soils. And looking at a level 3 assessment, which considers the dissolve phase contaminant migration within the aquifer itself, the K value influences the degradation potential for contaminants, with more permeable soils resulting in faster contaminant migration, and as a result, a reduced potential for degradation. So looking at our next case study, when we're assessing in-situ hydraulic conductivity tests, how do we do this? It's most commonly completed via what we call a slug test, which was namely the introduction of a slug of fixed volume into the water column in a monitoring well, which results in an instantaneous change in water level, and then we monitor the change in water level with time as it recovers back to the resting groundwater level. A minimum displacement of the water level is required, ideally higher than 0.5 meters, but at least 0.3 meters, in order to make sure that we're testing the aquifer rather than the surrounding gravel pack of the well. And as such, it's important to note that traditional slug tests may not be suitable for very high permeability aquifers, as recharge may be so fast that recording the change in head cannot be completed sufficiently. A couple of important points when considering slug tests. These are localized tests used to determine the aquifer characteristics, and we need to make sure that we optimize the robustness and the value of the test data as far as possible. To do this, we need to make sure that the wells have been previously developed and then left to stabilize prior to testing. It's important to complete duplicate tests at each location to demonstrate repeatability of the data set, and these duplicate tests should incorporate both rising and falling head tests, as the recovery of each of these tests targets the saturated aquifer and the unsaturated zones respectively. Spatial heterogeneity of the aquifer also needs considering, so we need to complete tests at multiple locations on the site if possible. And most crucially, and often forgotten, is the fact that the assessment of slug tests is based on a logarithmic scale, and so a high frequency of measurements at the start of the test is crucial. So on this basis, it's important to consider the anticipated geological conditions, i.e. whether we're going to encounter cohesive or granular deposits, and then whether or not we need to be using electronic pressure transducers to monitor the recovery of water level, or whether we can manage this through manual measurements. So looking at our third case study, a former factory site in Fife. This site was underlain by cohesive soils comprising a clay sand and sandy clay. Slow groundwater recharge was anticipated due to the cohesive ground conditions. And on this basis, the slug tests were completed using manual measurements rather than automated measurements, considering budget considerations versus the level of risk anticipated at the site due to the lower permeability material. So the literature values for a sandy clay range across 4 orders of magnitude, whereas completing the on-site slug tests allowed us to constrain this value down to within a single order of magnitude. The benefit of completing the slug tests therefore showed us that the hydraulic conductivity could be constrained to reflect site-specific conditions, thereby giving increased confidence in the model results. However, in this instance, the limitation of completing the tests using manual measurements was that the earliest part of the data set, so the first 10 to 15 seconds, was actually missed, and therefore there was a potential that we could have been under-predicting permeability if we had solely relied on the site-specific value. So to take this additional uncertainty into consideration, a sensitivity analysis was completed as part of the DQRA, and during this analysis we varied the hydraulic conductivity by several orders of magnitude to test the results on the DQRA predictions. The second site where we completed some slug tests was a petrol filling station in Aberdeen, and in this instance the site was underlain by granular sand and gravel deposits. So on this basis, faster recharge was anticipated, and the slug tests were completed using pressure transducers set up to record water levels on an automatic basis at 0.5 second intervals. However, crucially, we also used manual measurements as a backup just in case of equipment failure. Similar to the first case study, the slug test at this site enabled the site-specific value for the permeability used within the DQRA to be constrained down to within a single order of magnitude variation. However, in this instance, whilst we were able to capture the early data set due to the use of automated loggers, we were only able to achieve minimal displacement of the water column due to the highly permeable nature of the strata, and therefore there is a potential that the results weren't necessarily reflective of wider aquifer conditions. So to manage this additional uncertainty, calculations of the K value were also completed using the transmissivity and the aquifer thickness, the saturated aquifer thickness, and the sensitivity of the model results to variations in the K value were also examined through the DQRA sensitivity analysis. So moving on to our final point, looking at the resource potential of a groundwater body and how that can affect our remedial options. So regulatory guidance on setting compliance points in a DQRA states that it may be justifiable to increase compliance point distances in a number of circumstances, i.e. beyond the default 50-metre point initially required if we're dealing with hazardous substances that are already present in groundwater. Sustainability assessments would also come into play at this point, considering whether or not there is an overall net benefit or impact from any potential remediation that may be proposed. However, and crucially, extension of the compliance distance can only be done if there is credible information to demonstrate a significant physical constraint on the ability to use the groundwater resource in question. And these constraints can include where there's a present or future planned land use that limits the exploitation of the water resource for the foreseeable future, such as the presence of sewered urban areas, forest, or major infrastructure development. Topography can also limit the feasibility of a water resource being exploited, so steep or inaccessible land or areas with unsuitable access, and also natural limitations such as potential aquifer yield or the natural background water quality. In some instances, it might be that the water quality is so poor that requirements for treatment would render future development of the groundwater economically less viable or unlikely. So for the next case study and final case study, we're going to look at this last constraint, the implications of natural limitations on groundwater body resource value. So the final case study is a former fuel storage depot in an area of reclaimed land adjacent to the coast. Intrusive investigations completed at the site had identified that fuels had been released from leaking fuel lines and spills at the site. Remedial works had removed in the region of 6,700 kilos of hydrocarbon contaminated soils, and L-napple had also been detected during the remedial works. This had been removed as far as possible based on visual evidence and no observable L-napple remaining within the wells on the site. However, following completion of the remedial works, elevated concentrations of petroleum hydrocarbons remained in the groundwater in the made ground and the principal limestone aquifer beneath the site. A detailed quantitative risk assessment had been undertaken using default compliance points, and this had concluded that groundwater remediation was required in order to achieve the target concentrations derived from the site. So in order to refine the controlled waters risk assessment, we first completed a simple qualitative assessment of the aquifer's resource potential. This included investigation of desk study information that identified that the site was actually within a 5-kilometre buffer zone where there was a threat of saline intrusion affecting water quality. And on this basis, if the groundwater abstraction was to be proposed in the future, license restrictions were likely to apply. And again, it was considered unlikely that a groundwater resource extraction, particularly for potable supply, would be granted licensing on this basis. Furthermore, the site was also located within a heavily industrialised area on reclaimed land, and therefore there was the likelihood that the groundwater quality was impacted on a wider scale that would further reduce the feasibility of future groundwater abstraction. So following the initial qualitative assessment, we moved on to perform a cost-benefit analysis of various remedial options. To complete the assessment, it was first assumed that groundwater beneath the site is worth 10% of its pristine potable water supply value due to the inferior nature of the background water quality. A comparison of the aquifer value was then made against the various different calculated remedial options, and it indicated overall that the remedial costs significantly outweighed the assumed worth of the aquifer beneath the site. So following a subsequent sustainability assessment and assessment of natural attenuation potential, which indicated that the plume beneath the site was shrinking, it was agreed with the Environment Agency that remediation was not required or justifiable. And this therefore demonstrates the value of considering the resource potential and managing the uncertainty with regards to the groundwater in question, rather than taking a more generic approach. So just to summarise, when we're managing uncertainty groundwater risk assessment, good quality data is fundamental to the understanding of our aquifer characteristics and the generation of a realistic model of groundwater plume migration and the assessment of risk. Understanding the hydrogeological contextual site model is key to enabling appropriate assessment points and assessment criteria to be derived for each pollutant linkage. During this assessment, consideration should be given to designing suitable investigations, including site-specific data that will enable these sensitive hydrogeological parameters to be constrained within our risk assessments, including aspects such as the degradation conditions and the hydraulic conductivity of the aquifer. Any remaining uncertainties and limitations that are still outstanding within the conceptual site model should also be considered as part of our DQRA through aspects such as sensitivity analysis and model calibration, or else targeted via additional investigation and/or assessment. So, thank you very much for your time. And I'm going to switch my camera back on.
Thank you, Mel. Really interesting talk. We'll get straight into some Q&A, if you're okay with that.
That's fine.
First of all, okay, what's the minimum number of monitoring wells and rounds of data that you would need to characterise an aquifer?
Okay, that's a fairly open-ended question. It fundamentally would come down to our conceptual site model, how complex the ground conditions are that we're anticipating beneath the site, and the level of risk that may be associated with the site. So it goes back to the preliminary risk assessment and developing a really robust conceptual site model right from the outset that allows us to determine which areas we're going to potentially be the risk drivers and where we need to target subsequent investigation works. It might be for a complex site that we need to consider a phased investigation, but the key point is always going back to our initial conceptual site model, refining our understanding, and then identifying the uncertainties and the data gaps as we go through, and trying to refine those as we go through. And if we do end up at the DQRA stage and there are still uncertainties that we haven't been able to bottom out, that's when the sensitivity analysis and things would come in that allows us to then test the robustness of those assessment conclusions and the implications for the conclusions and the recommendations that we're making. So yeah, no simple answer, but conceptual site model would be the fundamental point to go back to.
Okay, how would you place a value on an aquifer for cost-benefit analysis purposes?
Yeah, so in the case of the case study, we went back to looking at the water rates, so the cost that you would be charged if you were to advance a potable abstraction in the area. You would be charged based on your cubic meterage of groundwater abstraction, and using that rate and assuming a fairly low rate of abstraction given the aquifer conditions. we were able to place a financial value on that water resource, and then reduce that resource value based on the water quality that we understood to be present. And then also, although not specifically considered within the cost benefit analysis, there was the additional factor that given the reduced water quality, there would likely be additional costs associated with treating the groundwater. So we looked at the pristine water quality based on the abstraction revenue, and then reduced that to 10%.
Okay. Please can you advise on where the figures to value groundwater are obtained from?
So what? Sorry, the figures.
Yeah, I think you sort of
is that possibly the same question? Yeah, similar question.
Just worded in a different way. What time scales does natural attenuation assume? Is it clean up over decades?
It'll come down to the site-specific setting. I mean, when we're looking at DQRAs, for instance, and we're looking at contaminant migration timescales, there is guidance within the Environment Agency remedial targets methodology that talks within basically if your proposed contaminant migration timescales are in excess of 1,000 years, then that's considered a reasonable time frame. When it comes to natural attenuation and considering reasonable time frame for that to occur, it's very much going to come down to a site-specific setting and the level of risk of the surrounding receptors, and what's proposed on the site as well.
Okay. Well, the question about which software do we use to assess the results of the slug tests?
At RSK specifically, we use a software package called aquifer, but there are various other software packages out there. But it's a case of making sure not necessarily just the software package, but also the various different analytical solutions that are available. So the examples that we used, we're assuming the Bauer and Rice methodology, which is for an unconfined aquifer, but there's various different analytical solutions that you can use depending on whether you're dealing with a confined aquifer or a semi-confined aquifer. So the key thing is making sure that we're using an appropriate solution rather than necessarily which software package we use.
Okay. Is the 50-meter compliance distance from the site boundary? Is the compliance distance 50 meters from the site boundary, I guess?
Specifically, it's from the outer limits of the plume, as opposed to the site boundary. So if you've got a very large site, then quite often that 50-meter point can fall within the site boundary. But it does also depend. So I know, for example, in Northern Ireland, quite often because in the absence of Part 2A, the main mechanism for dealing with contaminated land is through the planning process. And within the planning process, you only have jurisdiction up to the site boundary. Quite often the compliance point would be based on the site boundary as opposed to the 50-meter point. But in terms of the letter of the guidance is talking about 50 meters from the outer extent of the plume, the contaminant plume.
Okay. Brilliant. Well, thank you, Mel. That's all the questions that we have in at the moment. So I'd just like to thank you again for a very interesting talk. Hopefully you can all join us again next month. Details of our next webinar should be in your inbox shortly. So I'd just like to say thank you again and enjoy the rest of your day.